Hi everybody, how's it going? I'm super excited to be here with you today at GopherCon. My name's Kevin Burke. I just became a dad 7 weeks ago. I've just fed the baby and put him to sleep. So hopefully we've got about 30 minutes today to get into build and test caching. Let's jump right in. What is a cache, you might be asking? For me, a cache is an extra copy of something that you make locally to get you a result a little bit faster. Generally, you do it when you have things that are either far away or take a long time to retrieve or are really slow to compute, right? So when we have a local copy, we can speed up our operations considerably by avoiding doing computation or avoiding needing to travel really far to go get a result. For build caches in particular, we're more focused on avoiding slow to compute. So we want to make sure that we're only doing something once and that if we have a result, we're able to reuse it in subsequent steps of the build. A simple algorithm for caching, there are several different ways to do caching, but one of the simplest ones is, first step is you compute a cache key, right? And the key should be unique to the object that's in the cache. Once you have a cache key, you search in the cache for the key. If you do find an object in the cache, you return that result. If you don't, then you have to do whatever the slow thing is, the computation. And once you do the computation, you can save the object in the cache and return it to the caller. Let's look at some build caches. I'm really excited to share with you today. We're going to look at 3 different caching systems: Make, Bazel, and finally, we're going to look at Go, Build, and Test caching. Make was invented in 1976. It's one of the earliest build tools. The advantage of Make is it's on every machine, and it's very easy to get started with. I've set up a sample project, which is a very simple HTTP server, which loads a single template from the templates directory. The template is saved on disk as an HTML file and loaded into the Go program with Go bin data. We're going to use Make to build this project. Make has a concept of targets and dependencies that are used to build those targets. We declare the target on the left side of the colon and the dependencies on the right side. Let's call the binary that we're going to build GopherCon. If we wanted to use Make to build the GopherCon binary, we would let GopherCon be the target, and all of the input files would be dependencies, in this case main.go and bindata.go. And then to build the GopherCon binary, we invoke gobuild. Let's run that now. To run Make, we call Make, and then we give it the name of the target that we want to build. In this case, GopherCon. We can see Go Build is invoked, and now we have a GopherCon binary. Now let's see what happens if we run it again. Make tells us that the GopherCon target is up to date, and it didn't actually invoke the Go Build command. How does it work? How does Make know that it doesn't need to rebuild the command? Well, Make looks at the modification times of each file. If the target is newer than the inputs, Make does not rerun the command. We can check the modification times with the stat command. When we look at main.go, we see main.go was modified shortly after midnight at 12:02:37 in 37 seconds. If we look at the GopherCon binary, we see that it was modified at 12:09 and 11 seconds. Since the GopherCon binary is newer than main.go and bindata.go, we conclude that we don't need to do anything. You can also chain dependencies. We can add the Go bindata process as part of the dependency graph like this. Since bindata.go is a generated file, we put bindata.go on the left side, and we put templates index.html on the right side as the dependency that is used to build bindata.go. Now let's change this templates file and see that we rebuild bindata.go and then rebuild GopherCon. You can see here that we ran go bindata before building the GopherCon binary. And we can see that if we run it again, it will say that the target is up to date. You can imagine adding more complexity from there, for example, building up an entire program. However, make has some downsides. If you change the command that's run, let's say, for example, we want to run this with the race detector on, you won't get the files to be rebuilt. Make will still tell you that the GopherCon binary is up to date. If you check out an older version of source, let's say you check out a different Git branch that still has an older version of a dependency than the target program, Make won't rebuild the target. That's a downside of using modification times as the tool to determine whether or not a package needs to be rebuilt. Finally, you have to redeclare the dependency graph that Go gives you for free, and you might get it wrong. You might miss an input. You might add an input twice, or you might only test one code path that's possible through a dependency graph. That's a summary of Make. It's very easy to get started with, but there are also some downsides to it. Bazel is a build system that was written at Google to build large C and C++ applications more quickly and later open sourced. Bazel's goals are, number one, reproducibility. Everyone should be able to reproduce the same build artifact, which means being really careful about removing the differences between different people's environments. Number two is speed. Bazel wants to avoid doing work if it doesn't have to do it, and it wants to be able to do as much as possible in parallel. Here's the Bazel configuration for an example Go project, one of my projects. It's a completely different way of looking at things from Make. These configuration files are written in Starlark, which is a language that also goes along with Bazel. An interesting thing about Starlark is it is guaranteed to terminate, which means it is not Turing complete. This means you can use if statements, but you can't use while statements and you can't use recursion. It's also extremely explicit about dependencies. It's difficult to get started with Bazel without adding your entire project to Bazel. Here I'm downloading helpers for the Starlark language, the rules to download the Go project, and helpers to help with this build.bazel file on the right side. I'm also have to list every dependency of my project in the Bazel workspace. On the right side here, I have a build.bazel file. I have one of these for each of the Go packages in my project. And inside here, I have to list not only all of the source files in my package, but all of the test files as well. And I have to declare these as separate projects. So it's very, very verbose and very explicit. So let's go ahead and build this. You can see we're starting a local Bazel server. That's what implements a file cache. So the data gets cached in memory. You can see that we had to fetch the Go SDK and download the Go SDK. It's now fetching all the third-party dependencies for the project. In just a second, it's also going to fetch the Java JDK. So when Bazel says you have to be explicit about dependencies, it means really, really explicit. It's going to really download every single thing that it needs in order to build your project and store it alongside the project in the project workspace. So once it does all this, it's going to produce a dependency graph of all of the packages in my project. And then it's going to build a hermetically sealed build to the max extent possible. Normally you have to use something like Docker in order to isolate differences between environments, but Bazel is careful enough about how it sets up workspaces and how it sets up environment variables and how it eliminates differences between environments that it's able to do this natively on your laptop. Now finally it's building. You can see there's a lot of stuff going on. You can see each of these subcommands that's running are pretty explicit about what's actually being run. Now it's finally completed the build after 70 seconds. If we run it again, we can see it's much, much faster. It runs in about 330 milliseconds. So now if I look in the project directory, I have these 4 symlinks, bin, knackle, out, and test logs. Let's go and look at one of these just for fun. Bazel bin. We have these .a and .x files, which are artifacts. And I can see here, it did actually build some of the commands in this project. So if I run this, I can see here that I'm actually running the command. So Bazel actually built the Go binary that I wanted to use. So how does Bazel cache builds, and how does Bazel implement incremental caching? In Bazel bin, all these outputs are language dependent. So Go is going to have a different way of caching stuff than a Java project or a C project would. Bazel is going to use these .x files here. These are kind of subsets of the .a files. What Bazel does is it takes out of the .a files the parts of the .a file. Excuse me, let me back up a second. These .a files are archive files. So it's everything, all of the object code that you need to implement the Go package. And then the way that Go does a binary is it's going to link all of these together. This .x file is a subset of the .a file with all of the information in the .a file that you would expect to change from build to build. So Bazel is going to use this .x file as the cache key. Each build, Bazel will check if the .x file is up to date, including all of the dependencies, and if not, it will recompile the package and generate a new .a file. Bazel is like an F1 car. It's really powerful, but it has a lot of startup cost, and it takes a lot of tuning to get right. It can be really useful for your project, but it might not be a good fit. One other disadvantage of Bazel, the cache is enormous. A ton of stuff is in the build cache, including an entire copy of the Go SDK and the JDK. This can make it really difficult to have fast builds on systems like Travis CI or GitHub Actions, where the entire cache has to be downloaded from something like S3 on every build run. To implement build cache speedups, you really need to put the cache behind a persistent server. This is trivial for Google, tougher for GitHub Actions or Circle CI or Travis CI. Next, we're going to look at Go, which strikes a balance between Bazel and Make. Go build caching uses a lot of the same semantics as Bazel caching, but has the advantage of only needing to build Go programs. What should we put in the cache? We could cache the entire program, we could cache functions, we could cache individual files. Each of these would imply different trade-offs about how often we're looking in the cache and how frequently we would hit values in the cache. Go caches at the package level. This is a natural fit because we already build object files, these .a files here, for each package. A Go binary is created by linking all of these .a files together. Now that we know what we are storing in the cache, we need to build a cache key. How does Go compute a cache key? Well, any input to a package or to a program that could generate a different .a file must be included as an input to the cache key. If the input does change, we must make the cache key different because the .a file would be different, and we need to force Go to rebuild the package. So you can see I've put this in pseudocode here. We need some function that is going to operate on all of these different inputs and kind of put them all in a soup and spit out an output that's a cache key that will change any single time one of these changes. So Go uses a checksum. With basic ideas, we're going to concatenate all of the things that could cause the .a file to change and then compute a checksum from them. A checksum is a 32-byte value that makes it really easy to compare whether two values are the same. In short, if you change one character, the mathematical algorithm that computes the checksum will end up changing the resulting value so much that it ends up being completely different. You only need to compute the checksum once and you can use it for every comparison. So that way it's ideal. If you can imagine computing the checksum for Moby Dick, instead of needing to look at the entire file to compare if it changed versus a different file that you have, if you compute the checksum once, all you need to do is compare the two checksums, and it's a lot faster to do comparisons that way. Let's look at the simplest possible example of how to build a package and have it show up in the Go cache, which is a package with no dependencies. You can see here I've got a very simple package with a single constant. We're going to compile this package. We're going to use the special Go debug environment variable that will help us print out what the build cache is doing. So we've compiled the package. You can see here that Go debug is printing out a bunch of information. On the left side, you can see it's printing out that we're hashing this package with the given name. And on the right side, you can see there's a bunch of inputs to the hash. The first line you can see here, you've got the Go version. The second line, you've got the action that we're doing, which is compiling. The third line is the directory that we're compiling. The fourth line is the Go OS and Go architecture. And below that, we have a bunch more information about how the package was built. Then at the bottom here, you've got a checksum. This checksum is all the information that was written in the previous lines summed with SHA-256. Let's go look for that checksum in the cache. You can find the cache by running goenv gocache on your machine. You can see mine is I'm on a Mac, so it's in users Kevin library caches go build. And if we see what's in this cache, you can see there's a bunch of numbered directories. There are 256 of these directories. It's just the first two letters of the checksum. And what this let us do is split up the cache a little bit, so it's not all one big directory. This makes it easier to do concurrent writes and reads. So let's look for our file in the cache. Our cache file starts at 04 and 047. There it is. So you can see it exists in the cache. You see how it ends in -A here. This means that it's an action file. It's basically a pointer between one key and another key. So if we see what's in this file, we're catting the file right now. I'm just going to make it all fit on one line a little better. This is our checksum that we used previously. It's also the file name on the left side. This is a checksum of all of the inputs to the cache file. And on the right side, we have another checksum. That's a checksum of the .a file, which is the output file for the package, the object file for the package. So let's see if we can find this checksum in the build cache as well. This one starts with 11 and then 11.5. There it is. And you can see it's got a bunch of kind of junk data in it. And the reason it's got a bunch of this junk data is it's object code that's meant to be read by the computer itself. But you can see here that it's got a bunch of information that indicates this is the right data file. It's got the name of the file that we compiled. You can see here this ZZZZZ, which is the name of the constant that I set up. And so this is how the build cache basically works. We compute a bunch of checksums, and then we store those checksums in the build cache. If we run the compilation again, you can see that we should get the same hashes again. 047, we've got this hash here again. So, and you can see here that we didn't print out the name of the package when we compiled it because we already had it available in the cache. Now let's do a version of this package, but it has a dependency on another very simple package, this package on the right. How does that work? Go will build the leaf package first, package 2, in the same way as we built the base package before. Let's look at the compiled object file for package 2 in the cache. It has some important data in it. The first thing we want to do is get this checksum and find it in the cache. 83, 8391. So we have on the left side the checksum we just got, and on the right side we have the checksum for the data object. CD. You can see these two base64 encoded IDs in the object file. The left side is the checksum of the inputs re-encoded as base64. The right side is the checksum of the object file sans IDs. This base64 sum gets encoded as part of the checksum for the importing package on this line right here. You can see DR5, DR5. This way, if the dependency changes, the base64 code will change, and the dependent package will get a new checksum, which will trigger a rebuild. We can continue on like this until our entire program is built. It's turtles all the way down. Go also has the ability to cache test results. How does it do that? Well, test caching is just like build caching with a few tweaks. Let's compile this test program so that we can see it in action. The first thing we can see is that there's a lot more output on the screen. This is because to run a test, we have to import the testing package, which imports a lot of packages from the standard library. There's nothing that we can do about that. However, if we scroll up, we can find the most important part, which is the cache instruction for our test package, we can see that the package under test is considered an input to the cache for this test, simple package test. There's also this file in here called testmain.go. This is generated by Go, and it's what's used to actually run your tests. It's a main function that includes all of your other tests inside of it. The next thing we can see is that if we run the test again, the output gets cached. You can see here down at the very bottom it says cached. That means that Go didn't actually run the tests. It reused the output from the last time we ran the tests. For now, Go is using the exact same strategy that it uses in the build to decide what gets cached. It's looking at the package inputs and the files, and it's saying, well, I already built this and tested it before. I can reuse the cached input. However, one thing about tests is that they often have side effects. They load files or they read environment variables. If you change the time zone value in the TZ environment variable and rerun the tests, Go should not cache tests that try to create a time.time object and do math on it, or you'd be told that your tests were passing incorrectly. There are 4 syscalls that Go monitors for side effects in tests. We can see them all here in the guts of the Go source code: getenv, change directory, stat, and open. Anytime you invoke any of these syscalls, Go will write the names to a special log file for the test. Note that open does not care about files outside the module, Go path, or Go root. If you open a file in a temporary directory, Go won't attempt to add that to the cache. At the end of the test run, Go will read through the test log and look up the values for each key. For example, the modification time for a file we opened, or the value of an environment variable. I've modified our test to add 2 simple syscalls, so you can see that in action here. We can look up the test log by looking up the first test binary hash listed here, which contains a pointer to the test log. If we look up this pointer, you can see we have the test log here, which is very simple. A test log and then the list of syscalls that are added. Then we can see each of these syscalls being looked up on the lines below the test binary output. Finally, we generate a hash down at the bottom. This hash is combined with the test log output hash to form. This hash is combined with the test log, and the right side of the hash is the successful test output, this here, 5D8B. The next time we run the test, how does Go know that the files and environment variables match before it runs the test? Well, it does a trick. It will open all of them before the test runs this time, and then check that they have the same values as they did the last time we ran the test. We can see this when we run the test again. This time, we look up the values before we run the test, before we print out that we can cache the test value. We can see here that we're looking up the same environment variables and the same files that we were before, and we're generating the same hash CD7 that we did when we ran the test the previous time. If the file modification time had changed, or the environment variable had changed, these hashes would be different, and Go would conclude that it can't cache the test. And so that's how Go implements test caching. Here's a quick tip to make sure that you're caching your tests in a CI environment. The first thing you want to do before you build Go or run any tests is load the cache from where you saved it previously. Once you have the cache downloaded, you can build binaries and run tests. This will generate new artifacts that can be saved in the cache. Once you have built the binaries and run your tests and have new artifacts in the cache, you need to save the cache back so future test runs can reread those results. So make sure you are saving the contents of goenv gocache. Go is so good at build and test caching that that's all you really need to do to ensure that you're hitting the cache. Hopefully this will help you speed up your builds. Thanks very much. I really enjoyed looking at build and test caching with you today. I hope you did too. I'll be available to answer any of your questions in the chat room. Have a great day, and I hope to run into you soon.